Now, can we have such type of signals in practice so that we can use this whole advantage offered by differential PCM? The answer is yes. There are some modulating signal, the information signals, in which the two adjacent samples will be of very much similar values. And hence, in such a case, if I quantize the difference between the sample values, the range over which the differences are going to vary will be very small compared to the original range over which the sample values are going to change. And with the smaller range of signal, I can use lesser number of levels to quantize that particular signal, and hence I'll require lesser number of bits. With lesser number of bits, the bitrate of the signal is small and the bandwidth required will also be small. So differential PCM will obviously offer one very good advantage of lesser bandwidth requirements for the transmission of the signal. But let me bring one very important point into the picture. As we already said, differential PCM will be able to offer this advantage of requiring less number of bits only if the difference is varying over a small range. And this will happen only when the two samples are of very much similar values to each other. If the difference between the two adjacent sample values is large, then the range over which the difference is varying will also be large, and you will ultimately be using more number of bits for the quantization. So the very first point that we need to understand is differential PCM will only able to offer the advantage of lesser bitrate and hence lesser bandwidth if the original signal is such that the two adjacent sample values are not changing by large amount or not differing by large amount. Point number 2 that we have to understand is sometimes we may not have a signal in which the two adjacent sample values are close to each other. In such a case, to have two values close to each other so that the differences are small, we'll have to sample the signal such that the two samples are very much close to each other. If the gap between the two samples is large, then probably you cannot have the two samples with similar values. For example, if this is a signal and if I take the two samples like this, you can see the difference between them will be large. And hence I'll have to reduce the time gap between them by taking one more sample in between. And in that case, I'll able to reduce the difference between them also. Now, if you compare the original time gap and the new time gap, obviously the new time gap is smaller compared to the original one. That means TS2, the second sampling time period, is less than the first sampling time period. Now to have this, the second sampling frequency has to be greater than the first sampling frequency. And that means just to have smaller range of the differences so that we can use lesser number of bits for quantization, we are ending up taking more number of samples. If you're taking more number of samples, then obviously you will have more number of values to be quantized. And even when we are using lesser number of bits per value, because the overall number of values are more, we will require more number of bits in the quantization. So differential PCM will not give us that advantage if we are forced to use very large sampling frequency. I repeat why we would want to use large sampling frequency, so that the two samples are very close to each other and hence they have similar values so that their differences are small. So in this case, differential PCM may not perform any better than PCM. So that's the transmitter side. Now let's try to understand how the receiver of differential PCM needs to be designed. The digital signal will be transmitted through physical channel to the receiver side. The digital signal in the form of ones and zeros will be represented in the form of two voltage levels. I can use plus 5 volts for logic 1 and minus 5 volts for logic 0. There are many other representations also are available. When it travels through the channel, it will go through the attenuation due to the resistance offered by the channel. At the same time, the noise gets added to the signal which changes the voltage levels. When the signal reaches to the receiver side, there might be considerable change in the original voltage levels of minus 5 and plus 5 volts.